15.37 at 773 degrees Celsius, the reaction has a Kc value of 0.4. What is the Kp at this temperature? All right, so for this one right here, we're just going to use this equation. Kp is equal to Kc times R times temperature raised to the change in number of moles of gas. So they tell us what the Kp is. Actually, the Kp is what we're trying to find. So this is just going to be a plug and chug once we put in our values. Kc is what they give us, and they tell us that is 0.4. R is just a constant, 0.0821. And then temperature, we're going to convert 773 degrees Celsius to Kelvin, and that's going to give us 1046. And then we're going to raise it to the change in number of moles. And so up here, for products, we've got 1 mole of gas. So 1 mole of gas minus, we've got 2 moles of gas plus 1 mole of gas equals 3 moles of gas for reactants. So products minus reactants is 1 minus 3, and that's going to give us a -2. So we're just going to put -2 right there. And when we do this math across, we get the Kp value to be 5.4 times 10 to the -5. And that's the answer.
Okay, number 15.39 says calculate the molar concentration of water in A, 18 milliliters of H2O, B, 100 milliliters of H2O, and C, 1 liter of H2O. Assume that the density of water is 1 gram per milliliter. So this is a really, really easy problem. This is bringing us all the way back to like chapter 2. So it's pretty much just straight dimensional analysis. They give us how much water we start with. We need to convert that, and we want to have molar concentration, which is moles per liter. So they gave us our volumes. We need to convert that into moles, and then divide that by how much we have to get the concentration. So I'm going to start off with the density. It's going to give us, bring it into grams. I'm just going to do it for all three, because it's going to be the same step for all three. So for this one, we have to convert it to milliliters real quick. So same thing, density. So that crosses out all the milliliters. Now we have it in grams. So now we're going to use the molar mass of water, which is 18.02 grams. Grams. And we're going to multiply by that for all of them. And our grams are going to cancel out. Now we have it in moles. So we're going to figure out what that is, and it's going to be just plugging it all into a calculator here. Okay, so now we want some molar concentration, so we're going to divide it by the volume that it gave us. So in this case, it was 18 milliliters. And since molar concentration is in liters, we just have to do a quick conversion to liters. Same thing with this one. It was 100 milliliters. We're going to convert it quickly. this one was already in liters, so you don't have to do any conversion. It was 1 liter. And when we multiply those all out, we get the same number around the same number. When you round, it ends up being the same. And it's just showing that the concentration, the molar concentration of water is the same no matter what volume of water that you have. So that's the answer.
Right, 15.41, write the equilibrium law corresponding to Kc for each of the following heterogeneous reactions. So first thing we notice is in the instructions they say that we're dealing with heterogeneous reactions. That means we've got different phases with different phases of substances within the reaction. We're dealing with, in this case, solids and gases. And one important thing to remember is that the concentration of a substance in the solid state is a constant, meaning that if we increase the number of moles, we're also going to be increasing the the volume. And so molarity is a ratio of moles to volume. So if we are increasing both the moles and the volume, the concentration value is going to remain the same. And so because of that, we can discount or not include the solids in our equilibrium law. So this is going to be really easy. We're just going to be looking at the gases here. That is our important thing. And like always, it's going to be products over reactants raised to the coefficient. So for this one, part A, Kc is going to be just CO2, raised to the second power. And this marker is about to die out, so I'm going to grab another one really quick. CO raised to the second. And on the bottom, our only reactant that is a gas is oxygen, so it's just going to be oxygen. And no coefficient there, so that's that. For B, the Kc value, we look across and we see, oh, we've got one solid, but we've got two gases. We don't care about the solid, just concerned about these guys. So H2O times SO2. And then over here, on the reactant side, we notice that we only have one reactant, and that is a solid. So we don't have to divide by anything. It's just that, which is great. This Kc value, we're going to have CH4 times carbon dioxide all over concentration of water raised to the second power. Part D, Kc value is going to be, we're just concerned about the gases again, so H2O times CO2 divided by HF raised to the second value. So the exponent of 2. Over here, Kc value is going to be H2O raised to the 5 because this is a solid, so we don't worry about that here. And our reactant is a solid, so we're not going to worry about that either. So that's it.
Okay, this is 15.43. It says the heterogeneous reaction, shown here, has a Kc of 1.6 times 10 to the negative 34 at 25 degrees Celsius. Suppose that 0.1 mole of hydrochloric acid and solid iodine are placed in a 1 liter container. what will the equilibrium concentrations of hydrogen iodine and chlorine be in the container? All right, so for this problem, we're going to use a technique to solve it called an ice table. The way I like to set up my ice tables are right underneath the equation. So it's called an ice table because it spells ice. You start out with I, which stands for initial, and then C, which stands for change, and then E, which stands for equilibrium. I think I spelled that right. Okay. So what you do is you fill out the initial concentration, change in concentration, and equilibrium concentration for everything in the reaction. So the initial concentration of our hydrochloric acid was 0.1 molar. And then the iodine is a solid, so just like for our equilibrium laws, we can discount solids because it's a constant, the concentration. So we're just going to discount the solid. And then since these are the products, so initially there's none of them. So those are just zeros. Our change here, we're going to go from having 2 moles of it to having no moles of it. So it's going to be minus 2 of, we're just going to call it X. And then what you do to find the equilibrium is that you do this minus this. So it's going to be 0.1 minus 2x. And that's going to be the equation that we use to find the equilibrium concentration. Okay, so similar thing here. We know that we're adding 2 moles of X for the hydrogen iodine. So then when you do the same thing, you just take this and you make it into an equation. So it's going to be 0 plus 2x, so it's just going to be 2x. And then here, we just have 1x, so there's no coefficient, the coefficient is 1, so it's just going to be plus x. And 0 plus x, it's just going to be x. So then we're going to use all of this and the equilibrium law to figure out our concentrations. These are the concentrations that we're trying to figure out in the end. So all of the equilibrium concentrations, this one too. So first of all, we need to write the equilibrium, the law. So Kc, which they gave us, is 1.6 times 10 to the negative 34 equals, it's going to be products over reactants, and we can ignore the solid. So it's going to be Hi squared because of the coefficient times chlorine over hydrochloric acid squared because of the coefficient. So now basically what we're going to do is we're just going to plug in what we got down here for equilibrium with the x's and everything in, and then solve for x. So what we get is the concentration for Hi was 2x squared times x over 0.1 minus 2x squared is our constant. Now, because our constant is so small, that means that we can basically the change is going to be so small that we can just disregard the change to the initial one here. So we can just act like this is negligible because it's going to be such a small number that it's not going to affect 0.1. And in the end, even if we were to work it out like this, it would end up rounding back to 0.1 anyways with our significant figures. We can only do that when we have a really, really small KC. So we're just going to act like that's not there, and we're going to end up with 2x squared times x over 0.1. So basically, then we end up with 4x cubed over that's still going to be squared. I just square that. 0.01. And when we just use algebra with that and this, we end up with x equals 7.37 times 10 to the negative 13. So now that we know what x is, we plug x in over here to find out our equilibrium concentration. So our concentration for Cl2 is just x. So it's 7.37 times 10 to the negative 13. Our concentration of HI is 2 times 7.37 times 10 to the 13, negative 13, sorry. And that is equal to 1.47 times 10 to the negative 12. And then over here, we said that was negligible, which also you can see if you were to plug x in here and solve it with the sig figs that we get, we'd end up rounding back to 0.1 anyways. So the equilibrium concentration for our HCl is still just 0.1. And that is that problem.
How will the position of equilibrium in the reaction be affected by the following changes? Change number 1, adding CH4. So for this right here, what we need to keep in mind is Le Chatelier's principle. And basically he says anytime there's a disturbance in the reaction will naturally react in a manner to maintain equilibrium. So if we're increasing CH4 right here, that's going to drive this whole reaction forward, meaning that because we have more reactant, we're going to want to produce more product, which is going to shift it to the right. So for part A, the reaction is shift to the right. Part B, they ask us if we add H2. H2 is on our product side. So if we're increasing more product, that means the reaction is going to want to minimize this disturbance by producing more reactant. So increasing product means we're going to increase our reactant. So that's going to be driving the reaction to the left. Part C, removing CS2. So if we remove CS2, then the reaction is going to want to counteract by making up for lost product. So that means that the reaction is going to be driven to the right. So, right, because there's a decrease in product, we're going to want to maintain our balance, so we want to make more product, thus the reaction will be driven to the right. So part D, decreasing the volume of the container. So if we decrease, hold on, can you pause it really quick? Sorry. Okay, so if we're decreasing the volume, then we need to consider the moles of gas that we have. So looking at both our product side and our reactant side, which side has less moles of gas, and that is the reactant side. Over here we have a lot of moles. So if we're decreasing the size of the volume, and we have a lot of moles of gas on the product side, and that's going to drive the reaction to the left in order to, I guess, compensate for that and make sure that we have, I don't know, just like less volume or less gas. So anyways, so drives it to the left. A, B, C, D, E. E. If we're increasing the temperature. So in this reaction, they tell us that we have heat right here. So we know that we can consider heat as a reactant. And if we're increasing the heat, making more reactant, then the reaction is going to want to have more product. So that's going to drive us to the right.
Okay, 15.47. Consider the equilibrium. That's the equation on the board. In which direction will this equilibrium be shifted by the following changes? Change number 1 is adding N2O. So the way that I like to think about these equations, you're going to be using Le Chatelier, I don't know, it's French, his principle, and it's basically that if a system at equilibrium gets disturbed, it's going to do whatever changes it needs to do to get back to equilibrium. So the way I like to think about it is like a teeter-totter, or like a balance. That's like this, with something on both sides, right? If you add something to this side, it's going to tip down like that. You're going to have to add something to that side to make it go back to level. Right? If it gets heavy over here, you gotta add more over there. And if you take something away here, it's gonna pop up. And I was like thinking of the equation like a teeter-totter, where the little fulcrum is right underneath the arrows. So if you're adding N2O, it means this side's gonna get heavy, which means on that side, you need to add more of that to balance back out. So if you're adding more of that, it means it's going to the right. Change B is removing NO2. So in this case, for removing NO2, this side's going to get lighter in my metaphor. So if it's lighter, it's going to fling up. That means you're going to want to add more of it to make it back to level. So that means it's going to be going to the left since you're adding more reactant. Letter C, adding NO. So that's over there. If you add NO, that side's going to get heavy. So it means you're going to want to add more reactants over here to balance it back out. So if you're adding more reactants, that means you're also going left. D, there's increasing the temperature of the reaction. This can get a little bit tricky, but they gave us the delta H over here. So since the delta H is positive, then that means that the system is releasing heat, which means that heat can be considered a product of the reaction. So if you can consider heat a product, and we're increasing heat, that means the same thing. This side is increasing, getting heavier. That side needs to be increased to get it back to new level. So if we're going back towards the reactants, it's going to be left. E is adding helium gas to the reaction mixture at a constant volume. So adding helium gas, it's going to do nothing because helium's not going to react with it. Helium's not in the reaction at all. So adding more helium won't do anything to this system. It's kind of a trick question, I guess. There's no change. And for F, it says decreasing the volume of the container at a constant temperature. So for decreasing the volume, anytime we have a change in volume, we're just going to look at our number of moles of gas. So here we have 3 moles of gas, looking at our coefficients, and over here we have 2 moles of gas. So if we're decreasing the volume, it's getting smaller. It's gonna want to go towards the side that has less moles of gas, purely because then it has more room. 3 moles of gas compared to 2. If you're getting a smaller place and you want only 2 people in it instead of 3. I don't know. That's how I'm going to explain it. So it's going to be going over here. That's to the left. And that's that.
15.49. At a certain temperature, the Kc value equals 0.18 for the equilibrium. This reaction, suppose a reaction vessel at the temperature contained these 3 gases at the following concentrations. Compute the reaction quotient and use it to determine whether the system is in a state of equilibrium. If the state is not at equilibrium, in which direction will the reaction proceed to get to equilibrium? All right, so for this, we're going to be comparing the reaction quotient with the Kc value. So, equilibrium law tells us that Kc is going to be PCl5 over Cl2 times PCl3. And it tells us that that equals 0.18. Awesome. But right now, at this point in the reaction, they tell us that these are the molar concentrations that we have. So to find the reaction quotient, we're just going to plug them in. So PCl is 0.042, so we're just going to put that right here, times, we've got Cl, which is 0.0240, and we've got PCl5, which is 0.005. So when we do math for that, when we work that out, we find that the reaction quotient Q equals 4.96. And so because the Kc is not equal to the reaction quotient Q, we know that this, right now, this reaction is not in equilibrium. So and then the question, part B, they ask us, okay, so which direction is it moving? And because we know that the Q is so much bigger than the Kc, when Q is greater than Kc, then the system is going to shift to the left. So part B, it's moving to the left. And how do we know that? Because say we want this at equilibrium, the Q is going to have to equal Kc. So how do we get that? Well, the concentration of the reactants are going to have to increase in order for this fraction to get smaller. So that's how it is. Moving to the left.
All right, 15.51. At a certain temperature, the reaction shown here has Kc equal to 0.5. If a reaction mixture at equilibrium contains 0.18 molar carbon monoxide and 0.22 molar hydrogen, what is the concentration of, that's methanol gas. So they gave us Kc, they gave us the concentration of carbon dioxide, they gave us the concentration of hydrogen, so we really just have to plug those things in to solve for there. If we want to, we can rework the problem to get this solved for this. So all we do there is just time put this on both sides. So Kc times concentration from that side, concentration of H2 squared. That's going to give us concentration of CH3OH. We just plug in the values that they gave us. So it's 0.5 for Kc. And then it was 0.18 molar for carbon dioxide, monoxide side, and 0.22 molar squared for hydrogen. Molar. And then we plug all that in. Well, it is equal to our methanol. So when we plug all that in, we get we get 0.004356 molar. Sig figs is going to turn that into 4.36 times 10 to the negative 3 molar. All right, this is 15.53. It says at 773 degrees Celsius, a mixture of carbon monoxide, hydrogen, and methanol was allowed to come to equilibrium. The following equilibrium concentrations were then measured. And it lists the concentrations. Carbon monoxide is 0.105 molar, hydrogen is 0.250 molar, and methanol is 0.00261 molar. And then it wants us to calculate the Kc for the reaction. This is the reaction. So first we have to write out the law. Kc, that's the law. If you can't do equilibrium laws by now, just refer to our other videos. We've done it. All the problems in this chapter require this. They should be pro with this by now. So all we're going to do for this problem is just plug in the values that they gave us and plug them into the calculator. So for methanol, we got 0.00261 molar. For carbon monoxide, we got 105 molar. For hydrogen, we got 0.250 molar. And we plug all that in. You get 0.398 for your value of Kc. One thing I would say, just as a note, is just when you're plugging things in the calculator, just be careful. Sometimes you'll get not the right answer if you're not really careful about your, like where you put the exponent and where you put the parentheses and where you put the division. But other than that, this is a really easy problem. You just take the information, plug it in, solve.